Okay, here's an overview of the C6 topic, reversible reactions. Right, first of all, what are they? Well, a reversible reaction is simply a reaction that makes a product, and then the product can turn back into the reactants again. So typically we tend to see normal chemical reactions where you've got chemical A and chemical B and they join together to make something new. Well, sometimes we can get some reactions where once you've made a product you can turn back into what you started with again. So we get this constant cycle of backwards and forwards and backwards and forwards, and this all happens all in the reaction all at the same time. So reversible reactions, this is what they are, and you can spot them by this symbol here, and we call the top part of this arrow, this is the direction of the forward reaction, and the bottom part of the arrow indicates the reverse reaction. So now we know what they are, we're going to have a look at this phrase called equilibrium and what that means. So equilibrium simply means equal balance. Well, a balance of what? Before I come into what a chemical reaction is, a balance in a chemical reaction, I'm going to give you a real life example of what I mean by equilibrium. If we had a room, and inside this room we had an air conditioning unit and we had a small fire going at the same time, and if we placed a thermometer on the outside of the room to measure what the temperature was like, then we would see that the temperature would remain constant because the amount of heat being produced by the fire and the amount of cool air being produced by the air conditioning, they would basically cancel each other out and the temperature wouldn't change. So what we could say here is that we've got an equilibrium, we've got an equal balance of the rate of heat production and the rate of cold air production as well. And this is what equilibrium means, we've got an equal balance of something. So when we come back to chemical reactions, we can see in a reversible reaction that we get an equal balance of the forward reaction and an equal balance of the reverse reaction. So when the rate is equal to each other, and that's the important bit to remember, the rate, then we can say that reaction is in equilibrium. They're being made at the same time. And what that could look like on a graph is that we could see that the amount of A and B reduces, the amount of AB, which is our product, increases, and it gets to a point where the reaction levels off. Now, it could look as if the reaction has stopped because you're not making any more of your product, but that's just not the case. The rate at which you make your product is equal to the rate at which you're making this, so it looks as if the reaction has stopped. Problem is though is that if you're a company wanting to produce a certain chemical or get a certain product, you're going to get to a point where you can't make any more because of this equilibrium. So we need to change something about the reaction to make more of your product, which is going to be more profitable, and it also means as well that you're going to be able to get more for your raw ingredients as well. Okay, so let's have a quick look and see how that happens. We're going to change some conditions and that's going to alter how much we make, so we could get to a point where we're getting all the way up here somewhere. Before we do that, we've got one quick thing to have a look at, and this is something called Le Chatelier's principle. It's really simple. It just means that if a reaction happens in a sealed environment, in a closed system, if you change the conditions, then what happens is the system will change to counteract what you've just done. So going back to our example, if you look at our room, if we turn the fire up so the temperature increases, the air conditioning will increase as well to bring the temperature back down again. So we change something and the environment changes to bring it back down again, or we change the environment and part of the system changes to counteract that. So it's all about leveling off and bringing things back to as they were, equilibrium. So the Chatelier's principle, change a condition, the system will change to counteract what you've just done. So here's how we're going to have a look at this. We're going to take three different factors that can have an effect on the rate of a reaction, and we're going to see what happens when we play around with these in a reversible reaction. So the first thing we want to look at is high pressure. If I've got a reaction that involves gases and they're in the same size container, I've got chemical A, chemical B, here they are, I've got three of each. When they react, they pair up. So I've got from 6 particles down to 3. So in this container, I've got 6 individual particles that can hit the sides of the container. And that means I get a high pressure, compared to a low pressure over here because I've only got them in pairs. So I've only got 3 individual particles that can hit the sides of the container. So the collisions aren't as frequent, which means you're not going to get as much pressure inside that container. Therefore then, if I want to produce more of this, I don't want to create an environment that is low pressure because the reaction wants to be low pressure. I've got to do the opposite. I want to create a high pressure environment to encourage the low pressure reaction to happen. It's almost, think about it this way. If a reaction is high pressure, adding more high pressure is not going to help this reaction even more. All right, it wants to increase the pressure itself. Remember, it will do the opposite of what you're trying to do. So if you create a high pressure environment, the reaction is going to do the opposite. It's going to take some of that pressure away, and you're going to get this happening. If I wanted to produce this one, A and B individually, I would then create a low pressure environment, and what would happen is it would encourage the high pressure side of the reaction to happen instead. So you can encourage the forward and reverse reactions by changing the pressures around in a reaction, and this only happens with gases because there's gaps between the particles. You could change that. You could also change the temperature. So we just need to go over a couple of phrases first. The first one is the term exothermic, and the second is endothermic. Exothermic simply means that heat energy is given out of a chemical reaction, so it comes from the chemicals and goes to the surrounding, which means that the temperature increases. If we were to sketch this as a little graph to show what happens with the amount of energy our substances have, then we could see that our reactants have less energy than the products. Where does that energy go? To the surroundings, therefore the temperature increases. And endothermic is the opposite. In this case, what happens now is that the heat energy goes into the chemicals. Well, that's got to come from somewhere, so it comes from the surroundings. And if the surroundings have got less energy than when they started, that means the temperature must decrease. So exothermic gives energy out, endothermic takes energy in. The surroundings of the temperature of the surroundings increases, the temperature of the surroundings decrease. Now we know that, we can actually see that reversible reactions are exothermic in one direction and endothermic in another, and this can change depending on the reaction. So just like we mentioned here with high pressure and low pressure, let's do the opposite. If I want A and B, I know it's exothermic, it's going to want to give out energy. Therefore, if I put it in a cold environment, that environment is going to encourage that energy to come out of the reactants. This is going to warm up because the environment is cold. Simple as that. If I want to do the opposite, and I want to force the endothermic reaction to happen, then what happens here is I need to put plenty of energy into the environment. So if I make it nice and hot, there's lots and lots of energy to go into the chemicals, and as a result then we can produce A plus B. Remember, whatever we want to do, we change the environment so it is the opposite, and the reaction will counteract that. The only problem with some of this is that it could be quite slow. If you cool the environment down, your rate of reaction could be slow. You might get a lot of this, but it might take ages. So you've kind of got to get that balance right between the rate of the reaction, how fast it is, and the amount of stuff you produce. And the final thing we could look at is the concentration. This is really simple, this one. If you just want to make more of this, add more of this. If I wanted to make more of this, I add more of this. And that's it. So there's your overview of reversible reactions. We can see that we've gone from what a reaction is, down to equilibrium. Quick example of equilibrium and how it works with forward and reverse reactions. Quick look at Le Chatelier's principle, the fact that reactions will respond to counteract the change to the conditions. And then 3 examples: pressure, temperature, and concentration. So that's your overview of reversible reactions.